good morning, dear colleagues, dear candidate. Today we have a very important day because of now we will finalize a huge experimental and theoretical work supported by our Center for Materials Technology, Skoltech, and here is my greatest pleasure to introduce our candidate, Yulia Kuzminova, with her very interesting project, PhD project that she brought to our discussion, properties and characteristics of their chrome, ferrum, cobalt, nickel high entropy alloys and its modifications produced by additive manufacturing technique. And I'd like to introduce Yulia's supervisors, Professor Igor Shishkovsky and co-supervisor Professor Stanislav Yevlashin. And this project, this PhD thesis, is given in the framework of our doctoral program, mathematics and mechanics. So first of all, let me say a couple of words about the field of area, and then I'd like to introduce jury and jury members and our candidate. So first of all, as you know, the new frontier of material science has emerged with the introduction of high entropy alloys or multiply principal element alloys, as another word, as another term. Unlike traditional alloying approach, these high entropy alloys involves designing alloys with multiplying main elements, expanding the range of possible material properties. So maybe, as you know, the first published high entropy alloys demonstrated exceptional strength, ductile characteristic, firstly at cryogenic temperatures, and therefore it was proposed serious potential for microstructure design and application for extreme surface conditions. Moreover, high entropy alloys demonstrate very high melting point that made them applicable for refractory high entropy application with good potential to replace costly nickel-based alloys in high temperature regimes. So, however, it's crucial to explore these new materials using innovative production technologies that can contribute their unique characteristic. And therefore, our candidate highlighted applicability of these materials based on additive manufacturing technologies, particularly power bed fusion, and as you see, exceptionally interesting and broad study has been done in our center by candidate. And therefore, let me say a couple of words about Julia. Julia received her degree at Belgrade State University. So maybe you know that Belgrade State University has very good technological school, and there are a huge amount of technological ideas, new materials arise from this university. There are a lot of exceptional professors and researchers have been grown there. So then Julia continue his study here in Skoltech in our center, and finally, Julia decided to continue his study as a PhD student in the framework of our mechanics and mathematics program, doctoral program. So today it's our great pleasure to see and discuss PhD thesis proposed by Yulia Kuzminova. So a couple of words about supervisors. First of all, I'd like to introduce Professor Igor Shishkovsky. Professor Shishkovsky was, for a long time, he was a professor of our center. And in our country and abroad, Professor Shishkovsky is well-known expert in additive manufacturing technologies, working on huge amount of materials, metamaterials, introducing digital concept for design and technological performance of 3D printing process. As a co-supervisor, it's my great pleasure to introduce my colleague, Dr. Stanislav Yelashin. Dr. Stanislav Yelashin got his PhD degree in Moscow State University, Faculty of Physics, and now Professor Yelashin continue his work in field of high entropy alloys, gradient alloys, and also soft magnetic materials. Now I'd like to continue with introduction of jury members. As a chair, I'd like to propose myself. So now I'm a director of our Center for Material Technologies, and actually, frankly speaking, I spent more than 10 years working in Skoltech with the problem of experimental mechanics and material simulation and design. And now I'd like to support experimental study and theoretical investigation that was done in laboratory of additive manufacturing. So therefore, my laboratory and Stanislav Yelashin group, we have very close communication and a lot of joint work and publication. And now I'd like to start introduction of our professors, of our jury members. First of all, I'd like to introduce Professor of Department of Material Science and Nanotechnology of the Institute of Engineering and Digital Technologies, Professor Sergei Zhrebtsov. So let me say thank you very much, Professor Zhrebtsov, to join us today in this important day and for support of our research group. Actually, as you see, our colleagues, as you see, we have joint publication with Professor Zhrebtsov, and Professor Zhrebtsov, real expert in high entropy alloys, and as you remember, Professor Zhrebtsov also gave us a seminar a couple of years ago, where the idea of high entropy alloys was introduced to Skoltech, and then, frankly speaking, as I understood from this point, we start hard working on this problem, okay, jointly with Belgrade State University. So also, I'd like to introduce Professor Pinaki Prasad Bhattacharyaji from Indian Institute of Technology, Hyderabad. And thank you very much, Professor Pinaki Prasad Bhattacharyaji. Actually, as you see, we invite a lot of experts in the area of high entropy alloys and thermomechanical processing of advanced alloys, microstructure and crystallographic texture identification and study. Our next jury member from Novosibirsk State University, Professor Daria Lazurenko. Maybe you know, Professor Daria Lazurenko also joined professor in St. Petersburg State University, and her research interests lie in the field of intermetallic alloys and composites, protective coatings, and multi-layer structure. my greatest pleasure to introduce Professor Rama Subramanian Lakshmi Narayan, Indian Institute of Technology, Delhi. So Professor Narayan joined us in person. So thank you very much for this for your time to join us. Professor Narayan's research is focused upon understanding multi-scale structure property correlations in advanced materials such as metallic glasses and their composites, 3D printed metals and alloys and other functional materials. His main areas of focus are fracture, fatigue, and indentation mechanics. So I guess we'll have a lot of questions regarding these important mechanical issues from Professor Narayan today during our discussion. Also, let me introduce our last jury member. She's Dr. Tatiana Mishurova from Federal Institute of Materials Research and Testing from Berlin, as well known as the BAM Institute. Actually, we have very close collaboration with Tatiana Mishurova, Dr. Tatiana Mishurova and her research group. Actually, we have a couple of joint publications in the framework of their interesting topic for study of gigacycle fatigue behavior of additively manufacturing materials. And now Tatiana continue his study working as a postdoc in BAM in the field of material characterization, working with Professor Giovanni Bruno. So thank you very much. This is our jury members, and this is our candidate and candidate supervisor. And let me say a couple of words about our procedure and formalism. So candidate has 40 minutes, plus minus 40 minutes for presentation. And then we start questions from jury. So actually, after this discussion, each jury member is to confirm whether he is satisfied or not with the changes introduced to the thesis after the review. And then we're welcome questions from a general audience in Zoom and in our auditorium. So everybody welcome for questions. Then I will give word to supervisors, to Professor Igor Shuskovsky and Professor Stanislav Ilashin. Then we will take time for closed deliberation for this point, Zoom breakout room. So actually we'll have discussion among jury members, having some options for voting. And so on. I will introduce all these parameters separately when we come to this point. And then we welcome our candidate for outcome announcement. And then I guess we make a formal photo with appropriate suits for jury members. And now let me give a word to our candidate. Sure. So Yulia, you're welcome. Thank you very much.
Thank you very much, Professor Sergeyev. Thank you, professors and colleagues, for your coming, and for those who join us by Zoom. Second. Yeah. And today I would like to present the result of my PhD thesis, which called Properties and Heritage of High-Entropy Alloys and its modifications produced by additive manufacturing technique. And starting from the definition of the high-entropy alloys, they was first published in 2004. And according to the general definition for these alloys, it's alloys which are a single solid solution composed at least 5 elements in equiatomic portion. But according to the reports, which was reviewed in 2017, there are more than 600 reports demonstrated that this high-entropy alloys contains at least two phases. And today, the high-entropy alloys considered mostly like the new approach in alloy design rather than the strict definition. Anyways, it can be, today there are several compositions which can be considered as the most prospective. They can be divided by the two type of group, like single solid solution, multi-phase alloys. And in the first group, there are the 5-component system. It is first published, first demonstrated high-entropy alloys, and the high-entropy alloys with the 3 components. Also, there are the new direction which grow from the field of these high-entropy alloys. It's refractory, the high-entropy alloys with the refractories elements in their composition, and also which was presented by the composition which was presented by the group of the Belgrade State University, also used in their composition the refractory elements. It is like the multiple phase alloys. These two alloys demonstrate the extremely great characteristic at elevated temperature, but it's with has the limited ductility. So in our study, we're focusing on this these alloys, which calls contours alloys family, since they contains in their element in their composition like chromium, cobalt, nickel, and other alloys. And considering the properties of this 3-component system, it's see that this material has the really good strength characteristics at cryogenic temperatures, and it's demonstrates the higher strength characteristics in comparison to the 5-component system at the room temperature. And based on this system, this year NASA presented the new alloy with for the high temperature application. They prepared the pre-alloyed powder and compared the printed with using 3D printers, and compared the result of the oxidation resistant properties with the nickel alloys. And it demonstrates the better oxidation resistant properties, and even the tensile properties at elevated temperatures, at high temperatures, is higher in comparison with the nickel super alloys. So this alloy presented by NASA also contains the other elements, including the aluminum and titanium. And in terms of the specific strength of for this material, it's also the prospective system, since it demonstrates the good strength characteristics at elevated temperature. One of the publications demonstrated that they considered the set of the alloys where they varied the aluminum and titanium composition in this system, and demonstrated the good strength characteristics, but with low ductility. But still, at elevated temperature, it's still good strength properties, and even they observed the superplasticity effect. In comparison with the in the wide temperature, the properties of mechanical properties of this material in the wide temperature range, we can see how the strength and ductile characteristic evolves with the with heating at elevated temperature. So for the 4-component system, we see the tendency, then we lose the strength characteristics. But if we add alumina, we can stabilize it at elevated temperature and achieve the higher strength characteristics if we add the titanium to the composition. And it demonstrates the same tendency for the strength characteristics in comparison with nickel alloys, and also present the elevated ductility, the high ductility at elevated temperature. But still, it demonstrates the low ductility at room temperature. So this limits their application, and for the search of the required composition, there are combinatorial approach which can be applied to the searching and to optimize these strength ductile properties of these materials. And for this purpose, their additive manufacturing can be applied as the one of the most appropriate method. Additive manufacturing technique is the process which allows to produce the complex geometry of the part with saving the materials. But it has its own limitation for the application. With then we print materials. There is the strong residual stresses, and also we know that for the some composition, the chemical composition of the printed alloys is different than in comparison with the initial use powder. So since its technology is actively used in industry, it makes sense to adapt directly the chemical composition of the future alloy for the additive manufacturing application. And there was the work demonstrated, then there was presented the bench of the samples. There they varied the aluminum content in each samples and firstly analyze the phase composition of these samples and also mechanical characteristics. So today there are several metal additive manufacturing techniques. The material extrusion and binder jetings involve the print the solid parts with using the polymers, but it requires the additional heat treatment procedure after to remove this polymer from the solid parts. Sheet lamination, then we apply the laser or the heat source, hit the sheet of the materials, and with the vibration we wired our sheet of metals. And only two additive manufacturing techniques, direct metal deposition, powder bed fusion, provide the possibility like fully melt the materials and possibility to manipulate with the alloy composition. So the first is direct metal deposition technique. Then we used we can use the several feeders, so we can simultaneously print with different materials, and we apply our powder in the same place. We heat it with the heat source. It can be laser, it can be electron beam. And this is how we print layer by layer our solid part. Another technique is powder bed fusion. Then the thin layer of the materials spread on the platform, and according to the digital geometry, we melt the powder. So there's advantages and disadvantages of each technology. And if for the first case we can, this technology allows to print the big items and allows to print with using several materials simultaneously. So in case of powder bed fusion technology, it provides the possibility to print the complex geometry and with the higher accuracy. And also, specifically for this technology, due to the high cooling rates during the process, we can achieve the smaller structural objects. So here you can see the austenitic stainless steel, which consists of the cellular structure as the substructure on the substructure level, and we see that this cell surrounded by the dislocation. Also, we see that these cells are not homogeneous in doesn't have the homogeneous element distribution. And also we observed the small precipitators as like oxides in these cell boundaries. And for our purpose, we can actually use this cell structure provides actually the higher strength characteristic for these additive manufactured materials. And actually to improve also the strength properties, actually we can adjust this approach, and using the in situ alloying printing process, we can achieve the result. Then the secondary phase are formed on these grain boundaries contributes to the stretching effect of for these materials. And here the work we present then the alloyed the austenitic steels with boron nitrides, and you see the new phases forms around these cells. And also another work demonstrated the possibility to in situ printing with the powders of the 4-component system and aluminum, then the secondary phase absorbed on these cell boundaries. So the aim of our work is to investigate the structural and mechanical properties of this 4-component system produced with the powder bed fusion technique, and try to improve these characteristics using the in situ alloy which with the aluminum and titanium. And to achieve this purpose, at the first stage, in the first stage, we founded the required printing parameters for our 4-component system, analyzed the structure, and also analyzed the further post-treatments, how they affect to the structure and mechanical behavior of our materials. And on the next stage, we add the aluminum to our system and analyze the structural distribution and also phase distribution in this material. And also in the last stage, we observed the properties of the material alloyed with aluminum and titanium. So for this purpose, we used powder bed fusion 3D printers, 3 types of materials, 4-component system, aluminum and titanium, several microscopy technique, and X-ray diffraction analysis, and also mechanical test machine to analyze the mechanical properties of our materials. And the data structure can be divided by 2 parts. The first part focusing on the properties of this 4-component system, and the second part demonstrate the properties of the in situ alloyed materials. So coming to the part 1. In the first stage, we observed the morphology and the quality of the powder, and we see that the particle distribution is quite good for the PBF process. The element composition, according to EDX analysis, demonstrate the approximately equiatomic portion of each element, but the purity is about 99.7% with the 0.1% of nitrogen. And according to the, we prepared the set of the samples where we varied with the laser power and laser speed. And based on the result of the porosity and micro hardness, we choose one regime and continue work for these materials with this, mostly with this set of parameters. The structural analysis revealed the typically phase central cubic structure for these materials. It is elongated grains with the size about with the size of 50 microns in a longer side, and each relates with the size of the laser spore diameter and the distance between the laser tracks. Also, we observed the cellular structure, substructure, with the size about 0.5 or 0.7 micrometers. And according to the chemical, the analysis of the chemical composition demonstrated approximately the the homogeneous element distribution. X-ray diffraction analysis demonstrate the presence of the phase central cubic structure only. And also, which is typical for the additive manufacturing materials, it is the strong texture along the building direction. On the next stage, we analyze the mechanical characteristics in the wide temperature range of our materials at as build state and also in annealed state, since annealing is the common post-treatments for the additive manufacturing materials due to the strong residual stress in this material. And we applied the annealing at 150 degrees Celsius, which we choose according to the previous publication for this material. And according to the result, we see that the the strength property for this material is typical as for conventionally produced materials. Here we compared our printed and annealed materials with the four-component system, which was arc melted and further hot rolled. And the strength characteristics approximately the same. We don't lose in ultimate strength after annealing, but we see that the yield strength of the printed material is much higher, and we lose the only 100 megapascal after annealing, but it is still higher in comparison with the hot rolled material. Also, for the as-built materials, we observe the same tendency as for the hot rolled one, when we see the increase in ductility at cryogenic temperatures. Also, we expected the same for the annealed materials. We see that it increased at room temperature a little bit and at 300 degrees Celsius, but we didn't observe the increase in ductility at cryogenic temperature. The structural analysis demonstrates the formation of the small precipitates at along the grain boundaries, which was recognized as nitrates. And we assume that it's the main factor contributes to the lower ductility at the cryogenic temperature. But still, according to the X-ray diffraction analysis, we see that there are still phase central FCC phase observed even after longer heat treatment at 800 and 700 degrees Celsius. Also, we analyzed the properties of our material under the cycling load, and we observed, which usually observed for the additive manufacturing materials, that machine samples represent the better fatigue, higher fatigue life for the in case, if we removed the near surface defects. In case of unmachined samples, we see the difference between the as-built and annealed samples. Analyzing the fracture surface of this spacement, we see that for the as-built materials, the fracture surface is demonstrated like the brittle fracture, and for the annealed properties, for annealed materials, there are ductile behavior is observed, which associated with the residual stress removing. But back to the machined samples, as I said, there are the main contributor to the fatigue life is the formation of near surface defects. And here I would like to highlight that at near surface zones, the volume of the defects is higher in comparison, like with the inner printed materials. So it is essential to adjust it with the possibly the scanning strategy, or just remove these defects to increase the fatigue life of the material. On the next stage, we also decided to analyze the effect of the heat treatment on the material behavior. And for this, we annealed our materials for 24 hours at different temperature, starting from the 400 degrees Celsius till 1000 degrees Celsius, and observed the drop of the micro hardness after annealing at the 700 degrees Celsius. Also, differential scanning calorimetry demonstrated the endometric peak, which starts from this 400 degrees Celsius, and the another peaks, the middle of the peaks, like 500 and 600 degrees Celsius. The beginning of the peaks associated with the beginning of the moving of the point defects. Also, we observed the result of the in situ neutron diffraction analysis, which demonstrated that the peak width of the S-printed materials, it is the red dots, decreases started from the temperature 800 Kelvins, which is like 530 degrees Celsius. And it is associated with the relaxation or recovery process of this material, where the dislocation starts moving. And also we observed that even after such high temperature heat treatment like 900 degrees Celsius and higher, there are still the texture along the build direction which we observed, and they are not fully recrystallized structure. So according to this result, there are several temperature which can be indicated in the evolution, structural evolution of our materials, and we can observe that at this build state we see the cellular structure which are surrounded by the dislocation. Starting from the 400 degrees Celsius, we can assume that the point defect are started moving, or it can be associated with the recovery of the point defects. At higher temperature, at like 700 degrees Celsius, we see the drops of micro hardness and also the migration of dislocation and coalescence of our cell structure. So we see the disappearance of our cell structure at this temperature. And starting from the 800 degrees Celsius, we observed the new small grains, which can be the result of the beginning of recrystallization process. At 900 degrees Celsius, we see the moving of the high angle boundaries, and after even 100 degrees Celsius, we see the strong texture along the building direction. Also, we observed in the range of 700–800 degrees Celsius, and even using the transmission electron microscopy, we observed the small precipitates of this phase at 900 degrees Celsius, the precipitates of the nitrates, which associates the presence of nitrogen in the initial powder, which we used for our printing process. But still, even after long heat treatment, like 3 weeks, we see the formation of these new phases on the grain boundaries, even after annealing at 600 degrees Celsius. But interesting, we see the stability of the cell structure at this temperature. Also, we investigated the effect of the intensive deformation process on the material behavior, and for this purpose, we used the high-pressure torsion. This technique provides the possibility to use the small pieces of the material. We can achieve the high deformation process without losing of the materials, and also the result of this part of work can demonstrate how the properties of our additive manufacturing materials can be improved with this grain refinement techniques, and also consider the further application of our additive material in the harsh environment. So here you see the evolution of the grain size from the S-printed structure. Then the size of the elongated grain was about 50 microns, and after 8 turns it was about 90 nanometers. And we observed the hardness saturation of these materials the same. We observed that it was the same as for the S-cast materials, approximately with the same number of turn or the strain deformation level. Here's like 4 turns of our materials, and here's like 5 for the S-cast materials. Also for the our materials, we observed the phase central cubic structure only even after the 8 number of turns in our materials. Additionally, we observed the interesting properties for these materials with the in situ neutron diffraction analysis. For the HPT process materials, we observed that recovery and crystallization process occur at a lower temperature, but interesting finding that the dislocation density of this deformed material is lower at lower temperature in comparison with the as-built materials. So here it can be like the application of this finding, then we need to locally relax the residual stress of our material. We can apply the deformation process. It can be not high pressure torsion, but something different. When we refined our grain structure and applying the low temperature annealing, we relax only at this location our residual stress without touching the whole part. So here's the main conclusions for the part 1. I just want to highlight that according to our observation, we observed only phase central cubic structure at as-built materials, and no additional phases except then nitrates, which associated with the impurity of the powder, was found, like sigma phase or other. And the near surface defects have the crucial role in the fatigue life of our material. Coming to the part 2, alloying our system with aluminum and titanium, we start from the small aluminum addition to our 4-component system. And already we also prepared the set of the parameters with there we applied the different laser power and laser speed. And interesting observations that even the small aluminum addition leads to the lower porosity for the all considered regimes which we printed, which we used for the printing. But XRD analysis demonstrated the formation the FCC phase only, but we observed the shifting of the peaks of this of our material, which can be interpreted as incorporation of aluminum atom to the crystal structure. Still, if we observe the X-ray diffraction and the X-ray observation demonstrate the single solid solution, we see that the even with the we see the zones which enrich with alumina, which provide us the understanding that there are inhomogeneity in alumina in the chemical composition and in property also. So for improve the chemical homogeneity of our materials, we applied the high temperature annealing at 1200 degrees Celsius and observed that the for the 4-component system, we see the fully recrystallized structure with annealing twins. And in case of the materials with aluminum, we see the smaller grains for our materials. And also we did observe like these twins-like objects in the materials. Also, we see that the microhardness drops not such significant as in case of the 4-component, but still, according to XRD observation, we see the phase central cubic structure only. And also, we for the application of this material at elevated temperature, high temperature, it's essential to understand the oxidation resistant properties of our material. And for this purpose, we presented the three types of alloys, like the first one without aluminum, the second one with the small aluminum addition, approximately 1%, and 3% of aluminum addition, like smaller and higher aluminum content in our materials. And in case of the temperature of oxidation behavior at 800 degrees Celsius, we see the difference for the samples with aluminum and without aluminum, where we see the faster kinetics for our materials. But it can be related with the delamination process, which clearly observed in case of 1000 degrees Celsius, when we see the loss of the weight of our materials containing only four elements. But in case of in comparison for the samples with smaller and higher aluminum addition, we see that the kinetic observation for the material with higher aluminum content is higher. And according to the optical observation, we can see that the oxygen penetrate mostly through the grain boundaries of our materials, and the image which we observed for the smaller and higher aluminum addition is different. In case of this smaller aluminum addition, we do not observe the formation of these small precipitates as for aluminum with for the sample with higher aluminum content. So it can be indirectly represent the delamination of our material, which we didn't observe visually. But in case of material with higher aluminum content, we see the complex chemical composition of the near surface defect. For these materials, the initial powder contained 1% of magnesium, and we see the formation of the magnesium oxide as the first oxidized layer. And under this layer, we see the chromium oxides on the surface, the formation of the chromium oxide on the surface. It's related with the result from the X-ray diffraction analysis, and under this layer with the chromium and magnesium, we observed the formation of the aluminum, which generally prevents the further penetration of the oxygen in our structure and delamination of the material. But also we see here, you see the zones, they are enriched with alumina, but under the zone, we observe they also enriched with aluminum and nitrogen of our material, which also demonstrate the effect of the nitrogen, which was in the initial powder only about 0.5% on the material behavior at a higher temperature. And we observed the same thickness of these zones for the front and for the top view. So the oxidation process for the additive manufacturing materials occurs homogeneously. And in the last stage, we analyzed the properties of our materials, which alloyed with aluminum and titanium. And we compared, mostly focusing on the materials with the higher aluminum content, like 3.5 aluminum, and the aluminum with titanium, in comparison with the small and aluminum content and the 4-component system. And on the as was in the case of the small aluminum addition, in case of the materials aluminum and titanium, we observed the strong inhomogeneity, chemical inhomogeneity of our materials. And again, the annealing at high temperature can be suitable to improve this chemical homogeneity of our materials. But the scanning using the scanning process, like higher laser power or double scanning, doesn't provide the appropriate results. There are still, we see the inhomogeneous element distribution in our material. Analyzing the structure, so actually we wanted to achieve this idea, then we can form the additional phase on the cell boundaries, and it can be reached with the annealing at 800 degrees Celsius for the short period of time, like 30 minutes. Longer annealing leads to the disappearance of our cell structure, and also this like new phase boundaries. In case of the material of the as-built materials printed with titanium, we see even after short heat treatment, we see the plenty of phases formed during the as-built state and formed during the heat treatment. X-ray diffraction analysis demonstrated that in case of the small aluminum addition, no change are observed in comparison with the four-component system. If we add higher aluminum content at as-built state, there are the small percents of the new phase, but not really big with big volume, high volume, but this secondary phase stabilized during the heat treatment. But in case of the materials with titanium, we observe the formation of the new phase, its high volume even at the as-built state. And with further heat treatment, we observed also formation the sigma phase, the new phase, which was recognized as the sigma. And also we observed the difference of the microstructure for our materials with or without aluminum. Materials with aluminum only demonstrate the generally the same microstructure as for the four-component system, typical for the phase central cubic structure. But in case of the material with titanium, we observed the zones enriched with the small grains and those with the uniform grains. Analysis of these zones after heat treatment demonstrate these small grains consists of the BCC and FCC phase. So there are small size the grains of the one and of the two phases. In case of the material with aluminum, we see the formation of the new phases in the already formed grains. So to explain this phenomena, we prepared two phase diagrams for the aluminum and for the material with aluminum and with titanium, and observe the difference that in case of the materials with aluminum only, from the liquid, we see the formation only of the FCC phases. And only after the PCC forms from these solid phases from the FCC phase. In case of the material with aluminum and titanium, we see the simultaneous formation from the liquid of two phases, PCC and FCC, which explain the small grains of these two phases in the as-built material. So analyzing the tensile testing result of our material. It's presented only for the at room temperature. We see that as build state, the materials of the four-component system and with alumina demonstrate approximately the same strength characteristics. And only after heat treatment for 800 degrees Celsius for 30 minutes, we see the increase of the strength characteristic for the materials with the higher aluminum addition. But also demonstrate the drop of ductility. The same material demonstrate the drop of ductility at as build state, a further loss of ductility after annealing. In case of the material with titanium, we see the increase of strength in case of the as built material, and further with annealing, we see the additional increase in strength, but we totally lose the ductility even at the as built and annealed state of our material. Analysis of the fracture surface of our samples demonstrated the brittle zone which is associated with the brittle BCC phases, and also for the titanium, the materials with titanium, we observed the hot tearings in the as-built and in the as-built material. So comparison of our result with the early published work, which presented the mechanical characteristic for the arc melted composition approximately with the same chemical composition, we see that the we still has the low ductility of our material, even lower than for the arc melted material, and also we observed the lower strength characteristic in comparison with arc melted materials, and it can be a result of the hot tearing tears which are formed during the printing process, and it's for the further application of our this approach of the printing in situ. It's this challenge. Then the in printed materials there are several phases are formed in inhomogeneous material should be solved. So here's the conclusion of the second part, but I would like to mention like general conclusion of the work. And first of all, this work demonstrated that we for this four-component system we observed the typical behavior for the FCC materials. So the different solution which already exist for the other FCC materials can be adapted for the further work with this four-component system in case of additive manufacturing technique. Also, we observed that the nitrogen, even the smallest content, affect to the structural and even mechanical observation after heat treatment at elevated temperatures of annealing. So the purity of this of the material for the application at elevated temperatures key factor. And talking about the alloying of our four-component system through the printing using the powder plants, generally we can conclude that it's possible, and it's possible to improve this the inhomogeneity applying the high temperature annealing, but we observed the challenging that due to this chemical inhomogeneity or due to the specific of the due to specifics of this composition, there are several phases of form, and it limits its further application, demonstrate the lower mechanical characteristics than for the conventionally produced materials. So it also like challenge which should be solved in the future. So according to the result of this thesis, there are already 7 articles are published. One of them, the +1 manuscript under review right now in the Materiali journal. And yeah, thank you for your attention. I will be glad to answer your questions.
Yulia, thank you very much for interesting presentation, for good timing. So, colleagues, now I would like to pass words to our jury for questions and confirmation regarding changes introduced to the thesis after the review. So therefore, let me give the word to Professor Sergei Zhereptsov. So, Sergei, do you have any questions?
Yes, thank you very much. Thank you for very interesting presentation. Okay, I evaluated the work before, and I had several questions. I saw that many questions was answered during the presentations, but still, let's go to the 28th page. I just worrying a little bit about nitrogens in structure. Yes, that black dots at the BSE image. Yes. Are there nitrogens, or because this is as built structure, right? And those black dots at the BSE image, are there?
Yeah, yes, we recognize it's like the oxides or the pores.
In addition to nitrogens, you mean?
Yes, yes.
You mean you have nitrogen, oxides, and
yes.
and pores.
In the formation of the oxide is typical for the additive manufacturing technique, because even the small addition of the oxides, we observe it in the as-built states in any materials. So because of the yeah, it's like the essential for this material. And yes, we have the small precipitates of the oxides or carbides in our materials. It was in the article, it was presented like the carbides M23 carbide 7. It is built state. There are small particles like about 90 or 80 nanometers in size.
But why do you focus on nitrogens only? Because I guess each impurities have their own effect.
Because we see the difference in mechanical characteristic, and only after annealing and only during the annealing we see the formation of these nitrates around the grains. So we assume that it is contribute to the mechanical properties of our materials. That's why it's important. If it's possible, we can remove the oxides in the material of the as-built state, and it contribute to the properties of our materials, the same contribution to the material properties at as-built state and annealed state. And it's possible to minimize the formation of this oxide during at as-built state by using the another powder, another quality of the powder, but generally they are formed during the printing process. And so we, at the moment, we can't deal with the formation of these oxides. How huge the contribution, how the effect to the properties of this material, it's challenging to estimate, since it's anyway will be formed even at as-built state, annealed state, and other ways. So that's why I focus on nitrogen, because we see this only nitrogen effect after at elevated temperature. We do not observe this. We observe this oxide at as-built state and at elevated temperature. So if it's decrease our characteristics, so it's decrease in and for as-built material.
Okay, thank you. And just I'd like to follow my question. The next page. Why we see that decrease in mechanical properties for only one temperature, actually? 150, right?
Yes.
I mean ductility, of course.
Because in this case, there are at room temperature and higher, and in case of cryogenic temperature, there are different deformation process in the materials. So in case of room temperature and higher, the materials deformed with the dislocation slip way. In case of the cryogenic temperature, this mechanism is blocked, and not blocked, but the non-twinning deformation is absorbed for this materials at lower temperature, and possibly for this type of deformation, the formation of these brittle nitrites on the grain boundaries more important than in case of the slip dislocation.
Okay, thank you. Then another question is concerning high pressure torsion. I didn't hear your explanation now today. Why do you miss that, like usual deformation? Why is high pressure torsion, severe plastic deformation?
Why? Sorry, can you repeat?
You just like looks like you missed the usual deformation, usual rolling, usual upsetting, but you made a very huge step to severe plastic deformation.
Yes, because actually we decided that in case of the rolling or the other type of like cold rolling, cold forging, or hot forging process. First of all, we are limited in the deformation level, since each time it's technically challenging. As I remember, I did it. And in case of the high pressure torsion, it's easily to just by the number of the turns achieve the higher deformation. Also, if in these studies we investigated only the 4-component system, but for example, considering the further research, when we add aluminum or aluminum titanium, it is brittle materials. And we can apply this technique, for example, to analyze, is it possible to use it as a harmonization process, of a chemical harmonization process. And in this case, we deal with the brittle materials. For the high pressure torsion, it can be more high pressure torsion can be more suitable in this case than, for example, rolling with just fractured our materials, and we will not allow the high deformation, high deformations.
Okay, thank you. And the last question?
Your question?
Yes, the last one. Just your opinion. When you use power blends, is there an effect of melting points of each certain metal, each certain powder, or not? You try to use titanium and aluminum.
Yes.
They have quite different melting temperature. Is there an effect on homogeneity of distribution of those elements in the structure?
In powder blends, we have the mix of the 3 powders. But in the as-built materials, even if we observe the inhomogeneity, chemical inhomogeneity, we do not observe the zones which are fully, like fully titanium or with titanium material or aluminum. So we anyway with this homogeneity related with the phase difference also in the material. It generally it can affect the, for example, it should affect the melting process in the material. So the printing process should be adapted for specifically for this for this material, because we can look in case of aluminum 5 component system with aluminum in comparison with the 4 component system. So
okay, thank you.
Thank you for the question. So, and are you satisfied with the changes introduced in the thesis after the review?
Yes.
Yes, microphone to Professor RG from Professor, do you hear us?
This because all these are very highly deformed materials, strained to a very high deformation. So many of these alloys, Cantor and Cantor-derived alloys, there is a chance of sigma phase precipitation, particularly when you deform it to large strain and then anneal. So can you comment whether you have observed any sigma phase precipitation in these alloys?
I'm sorry, could you repeat the
last? My comment is that that many of these alloys are prone to sigma phase precipitation, sigma phase, particularly when you strain to deform it to large strain and then you anneal it. So this sigma phase precipitation is accelerated. So could you please comment that whether you have observed any sigma phase precipitation?
In our materials and in as-built one, we didn't observe sigma phase precipitation at as-built state and even after HPT process. But I should mention that other work which demonstrate the material arc melted or with further procedure. They also do not present the formation of the sigma phase for the 4-component system. Here's the difference with the 5-component system, which contains magnesium. We observe many publications demonstrate the formation of the sigma phase for these materials, and actually it was the one of the reasons why in the first hour publication we decided that this nitrates is the sigma phase. But analysis of the further works demonstrate that it is not. In case of this 4-component system, I know that for the HPT materials of the 5-component system, there are the formation of the new phase. I'm not sure it's sigma phase, but it's like they observed like kind of like trip effect in this material, but only after the surf deformation process, it was like 14 turns of the 40 turns in case of the high pressure torsion. And in this case, the max of our maximum is 8 turns. So maybe there are possible the formation of other phases, but in case of the sigma phase, we can just translate the result for the 4-component system to this from the 5-component system to this one, because the as-cast materials doesn't present the formation of this sigma phase for this 4-component system. But maybe the higher deformation process leads to the formation additional phase, including the sigma, so we didn't observe it.
Yeah. Yeah. So you did not observe it in the sense is that because I feel that sigma phase will be very small, almost in the nanoscale in this material, because its matrix is heavily deformed. So maybe the observation of the sigma phase is little more challenging unless you have really focused on that. So maybe this could be one of the interpretations of not having this, but anyway, this is debatable. My second question is that you have shown that there is a recovery in the after high pressure torsion. As you already are quite, as we all know that these materials are very low stacking fault energy materials, right? So I am just wondering that in the sense of recovery, what kind of recovery are you referring to? Because in the recovery also, as I see that there is a trend in the increase in the hardness. Okay, so what is this? What is the origin of this behavior? I mean, what exactly you mean by recovery here? Okay, particularly when your material is low stacking fault energy, and then what is the origin of the increase in your hardness in the recovery stage?
So in case, yeah, actually, I agree with you that actually the technique which we applied, we not observed, the reason why we didn't observe this nano-precipitates of possibly sigma phase, because our technical limitation of our microscopy analysis. I agree that yeah, possibly we need to go deeper and analyze more precisely the formation of this the new phases at this temperature of the recovery process of our materials. Yeah, it's actually very arguable, I agree, arguable conclusion, but still, since we made the conclusion that this stretching associated with the dislocation moving due to due to fact that we lose of this stretching effect with the further with the longer heat treatment. So, but I agree for analyze this phenomena, we need more precise microscopy investigation. Yeah, I agree with you.
Yeah, I think I also, yeah, I accept your explanation. You need to look into this phenomenon more deeply, particularly what is happening at your recovery stage. Okay. And second point is that you have talked about the development of a texture in your material after your in the as-built condition. Now, have you looked into that? What are the kind of anisotropy does it introduce in your built part? So, have you found any prominent effect of this texture on the anisotropy of your mechanical properties? Can you comment on that, please?
Sorry, we're talking about 4-component system or alloyed one?
No, I am talking of your 4-component system. So if you have a texture which is inherited from your inherited in your as-built part, so does it have a contribution towards the anisotropy of your mechanical properties? I mean, have you investigated or thought about it? Just you can comment if you have not investigated.
No, we didn't investigate. We only made the observation from the on only this part. Yeah.
Yeah, but do you think that it is going to have a strong anisotropy of your as-built parts? Because you have shown the presence of a texture. So I'm just wondering that whether it will also introduce a kind of anisotropy in your mechanical properties if you measure it from different directions.
General mechanical, observing this specific effect of the stretching of recovery, we observe only for the one direction. In talking about the mechanical property like tensile properties, we observed for the several direction. Here on the first slide, at the beginning of the our investigation, I presented the result of the mechanical characteristics at the direction along building direction. But in the end, we came to the understanding that we would like to work in transversal one and direction. And actually, yeah, it's these results are comparable, but still we observe this anisotropy mechanical behavior in our material. Yeah, definitely.
Okay. Okay, so do you have any idea, I mean, how to control this anisotropy? Because if you are going to have an anisotropy in different direction, this poses certain challenge. So do you have any additional comments on how you can control this anisotropy?
As far as we investigated, this anisotropy associated with the not only with texture but also with the residual stress in the material. So depending on the form of our material, actually the mechanical characteristics can be a little bit different. So there are several ways. The first one is they apply the high temperature annealing to achieve the full crystallization of our material, and in this case we reach the homogeneous mechanical characteristic at all direction. In case if we try to manipulate with the residual stress field in the as-built material, possibly it can be adjusted depending on the form of our part. In this case, maybe we can somehow adjust. Also, we can apply to minimize the residual stress the heating platform, but we need to be sure that actually this mechanical properties has the residual stress nature, because in case of the building the high part, we observed that there are several heat cycling process in this material. So in case of the kind of like flat part, the history will be different, and this affect to the material properties. So to understand it's the huge work of working on the understanding of the residual stress. So I believe that it is way how it can be solved, but actually anyway, we should anyway, there's a question: should we to minimize the this inhomogeneity of our mechanical properties? Maybe we can build a part with the which will be used in the specific direction, and according to this field of the using this part, we can possess our material, our part, and achieve the required mechanical characteristic at the specific direction. So there's like, do we really need to lose our inhomogeneity?
Okay. I think I have just maybe one more question, is that regarding your B2 phase in your aluminum, can you please go to that slide? Yeah. So here actually you have commented about the B2 phase formation on this. So your B2 phase is actually rich in what? Nickel and aluminum? The B2 phase,
yes,
you have commented about.
B2 phase, it's enriched with aluminum and nickel, and we assume it is specifically this BCC phase. It generally forms in case of the smaller, for the alloy, for this 5-component system with aluminum, in case with the small aluminum content. and higher aluminum content leads to the formation of the A2 BCC phases, so or two of them. But on the first stages, it's B2 BCC phase, and we see its enrichment with aluminum and nickel. But we didn't make the TEM observation of this phase, so I doesn't have the the TEM diffraction analysis to say this is exactly this B2 phase.
Okay. So basically you are not sure whether it is a disordered BCC phase or it is an ordered B2 phase, right?
We assume that is ordered B2 BCC phase, but for the strict conclusion, we need the TEM observation, which we not presented.
Okay. 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 So in terms of the chemical composition, you have determined the chemical composition, which shows that it is nickel and aluminum rich, right? You commented
Yes.
that it is nickel and aluminum rich. Okay. So just I have one question is that because there may be a lot of difference in the behavior of your alloy when because normally the B2 phase in such systems are quite hard and brittle as compared to your soft matrix. So I'm just wondering is that particularly, of course, it depends on how much B2 phase formation is there and etc. So can you please some quantification of that the fraction of the B2 phase what has been formed, because I might have missed that point, that what was our fraction of the BCC or B2 phase formation? Can you please comment?
Yes, and here again we need there's the challenging of this way of performing this material. So in case of the X-ray diffraction analysis, we can see that there are the small peak which can be associated that there are approximately 5%, but there are the problem that in the additive manufacturing material we have a strong texture, and actually we can directly calculate it from the X-ray diffraction analysis. In case of the EBSD analysis, we can estimate the percent of the formed BCC phase, but the problem that even we take this analysis from the big area, in this case, we do not catch the small particles. In case we take the small area, we observed only the small part of the formed materials. So here we see we observed try to observe the middle. Then it was 50 per 50 micrometers, and we observed about approximately up to 4 and 1% of the BCC phase. So there, to understand exactly the fraction of these materials, there should be the set of the EBSD tests at both directions at different magnifications. So in this case, in our study, we just demonstrated that there are the BCC phase and tried to understand the fraction of this BCC phase in comparison with the material with titanium. And we concluded, according to the BSD analysis, that it's approximately 4%. But I can't guarantee that strictly this number.
Okay. Okay. All right. So yeah, and yeah, I think I don't have any major questions for this. Just one comment is that I think my overall comment is that particularly this second phase can have a lot of effect, because this is somewhat a hard and brittle phase. So possibly the quantification, that how much exactly it is, what is the morphology and how it is distributed, because you have only observed from one direction. Maybe a three-dimensional knowledge of the three-dimensional distribution is important to understand the full mechanical behavior or the contribution towards the mechanical behavior. Okay. So yeah, that's it. And yeah, that's it from me.
Thank you.
Thank you very much. So let me thank Professor Barkhatarji for deepness of review, and let me ask a formal question for Professor Barkhatarji. Are you satisfied with the changes introduced to the thesis after the review?
Yes, I am satisfied because some of the questions that suggestions were, asked. I understand that this is based on the published papers, so which is not possible to incorporate. But other, I am so yeah. So overall, I am satisfied with the changes in the thesis.
Thank you very much.
Thank you.
So okay, we continue, and let me invite our guest from Novosibirsk State University, Professor Daria Lazarenko, for questions and comments. You're welcome.
Yeah, I would like to thank Yulia for the very nice presentation, and I would like also say that the work was very nice. It was a pleasure for me to read this thesis. Microstructural analysis was very beautiful, and the data obtained are quite valuable. And regarding my question, first, if you allowed, I would make one comment on the replies for my questions during reviewing. It concerns about oxidation tests. Mm-hmm. So my comment was that you should do the tests using crucibles, and asked what was the standard for the test. And you mentioned that it was GOST 613070. And according to this GOST, yes, you're right that it is possible to make tests without crucibles. However, in this case, you should measure not mass gain, but mass loss. So, and as you provided the mass gain graphs, for this reason, it's quite confusing. Yeah, so it's a short comment. I understand, of course, that you can't change these graphs in the published paper, but it's just a short comment. And about questions. So I have some questions on methods, particularly on neutron diffraction. First, maybe it's more philosophical question. You used neutron diffraction, but do you have some advantages? Do you get some advantages in using neutron diffraction compared to synchrotron diffraction in your case for your materials? So why this method was used, not synchrotron diffraction?
So it's this method provide. There are no for us for our purpose. It's not the big difference in case to using neutron or synchrotron diffraction, and for our purpose, it's the idea was to analyze the catch this moment of the change in the crystal structure to understand this material behavior. So yeah, the synchrotron diffraction can be used as well. So there, yes, no.
Yeah. And you mentioned in your thesis that it was time of flight neutron method. So, and it is known that when you get when you do these measurements, the peak shapes can be asymmetrical in this method. Unfortunately, you did not provide any pictures of the peak shapes. So my question is, did you observe this asymmetry of peaks? And if yes, how did you then apply Williamson-Hall method to analyze these peaks?
In case of the neutron diffraction?
Yes, yes. So you mentioned that it was time of flight and the shape of peaks is asymmetric usually. Did you observe this asymmetry?
I don't remember that we observed this asymmetric, but I can check and provide later, but I don't remember that there was problem. In case of the X-ray diffraction with Cuprum tube, we observed this, of course, the asymmetrics in peaks as usual, but in case of the neutron diffraction, I don't remember that we faced with this such problem.
Okay, thank you. And the other question, as you analyze all these effects in your alloys using diffraction as grain size and microstresses, but it is known that in multi-component solid solution, there is no exact lattice parameter, and it induces the increase in width of peak. So did you somehow separate this effect from the others when you analyze XRD patterns or neutron diffraction patterns?
Can you repeat? I didn't catch the point.
Yeah, okay. From the beginning. So when you observe this, when you get disorder solid solution like high entropy alloy, so you have no this stable, can be say stable lattice parameter. So it induces the increase of the peak width. And you also analyze microstresses, grain size, which also contribute in the peak width. So how did you separate these effects?
So in case of lattice parameters, we follow the position of this peak.
Yes.
And in case of the understand of the microstrain,
so in profile analysis.
Yes. Yeah. We use the half width of the height peak. So that's how we spread it.
Okay, thank you. So one more question. Maybe it's page 58, I think. 58. So you provided these nice pictures how BCC phase is distributed in the structure. Did you observe how sigma phase is distributed?
Phase we observed actually it's like between the small grains we saw, but we saw it's according only base E observation. So it's not TEM observation or then we obtain the TEM diffraction and strictly recognize it's like the sigma phase. But we suggest that we observe the sigma phase and it's forms between the grains, and after further heat treatment, there are the higher like grains or precipitates of the sigma phase.
Okay, thank you. I think I have no more questions. Thank you.
Thank you very much for your question, for detailed discussion. So I have four more questions. Are you satisfied with changes introduced to the thesis after the review?
Yes.
So thank you very much. Okay, so let me keep our good pace. So, and it's my great pleasure to invite Professor Narayan for questions. Professor Narayan kindly join us in person in this room. So please, your questions.
Thank you. Very nice presentation, and happy that you could finish everything within 40 minutes. I've never seen that happen, so that's good. And the volume of work is amazing. I have not seen a PhD student having so many papers in 4 years. So that's a great effort from you and your supervisors. So I just have some questions in addition to what I had asked earlier. And I just was seeing your slides. And if you go to slide number 27. 27. Yeah, 27. One more, yeah. Yep, this one. So I just observed that you have plotted this porosity, input density, input energy, and micro hardness. And I observed that, at around 700 or 780 joules per mm square, the data point of porosity, right? So it appears to be very porous, but it also has very high hardness. So why is the hardness also high along with porosity?
It can be the result of the with higher energy. There are possibly that then we increase the energy of laser or input energy. The nature of this porosity and then the material is boiled. But in this case, maybe we achieve the higher cooling rate, and maybe it can affect to the structure. But actually, I didn't. Unfortunately, I didn't add the arrow, so there are not. I would say it's not really big difference in this case. So it's approximately the same anyway. We have the higher error for the additive manufacturing materials in case of the S-build states, since there are, as you saw, the microstructure is very uniform, and we have the the elongated grains like 50 microns, and between these grains we see the finer structure with the grains less than 10 microns, and it's contribute to higher error, and in this case it can be just part of this.
So it's a part of the error. So also, where do you take these measurements? Do you take it along the build direction, on top of the sample?
On the top of the sample. So the build, and actually we even we polished without removing the samples from the platform, and then estimated the bench of the samples with optical observation, then just to go to the micro hardness testing machine.
Okay. I want to go to slide 32.
Mm-hmm.
Yeah, this is the one. Yeah, this is the one. You have shown that annealed sample has got a better endurance limit. I'm looking at the unmachined condition on the left side, and it has a better endurance limit, right? So my question is, first, I have a couple of questions, but first is, why is annealed sample better in terms of endurance?
For unmachined samples, you mean?
Yes, unmachined, yeah.
In case of unmachined samples, so there are, in case of the cycling loading, there are two stages of the sample fracture. The first is formation of the crack, and there the second stage is propagation. In case of the unmachined samples, we already have the formed defect which initiate the crack. So the first stage is really short for these unmachined samples. And so the main contributor to the fatigue life is the crack propagation time. And in this case, for the annealing samples, since we have the more ductile behavior, the fatigue life is higher and it's visible. In case of the machine samples, we spend more time to the crack formation. And in this case, since we deal with the higher stresses, higher loads, the propagation of the crack is not so not so sensitive. Plus, actually, it possibly that there are also the contributor like the formation of these nitrates. They may also contribute to the fatigue life, but it's just our assumption.
So here you have put, I think, arrows, right? I asked you questions on that in your comments as well. So you have 3 data points showing the runout, right? Runout condition for the annealed sample in the unmachined condition.
This one?
Unmachined. See, 3 red data points, right?
Yeah, yeah.
So what does that mean? I'm not sure if, so you have tested 2 more samples to verify, and what it appears is that it is going very close to the, the annealed sample is going very close to the as-built one, right? The endurance in one of these cases.
Mm-hmm.
So is this really a true indicator of the endurance limit? I mean, is it because this is heavily influenced by the presence of defects that you are getting this variation at the endurance limit?
So in case of these 3 data points, we applied the stress load, like approximately 200 megapascal, and we achieved this number of cycles. So we stopped the testing without fracture, without the damage of the samples. And then we started to move to the higher stresses, and that's why we achieved this, also these additional points.
So it doesn't break.
So it didn't break. So it doesn't mean that it didn't break.
So it's fine. So it's okay. So I think that is exactly the endurance limit.
Mm-hmm.
Got it.
So maybe in future, after additional cycles, they will break, but we don't know. So it's somewhere
maybe at 10 power 8 or 10 power 9. Yeah. So here, my only concern was you are, did you see any striation markings in your samples? Let us say the ones which failed. Did you see any stable crack growth regime in the fractographs?
Like stable crack propagation zones?
Yeah.
Actually, I saw the beautiful image for the high cycling fatigue testing. Mm-hmm. And they're like the the beginning of the image, and you can see these several zones. In our case, we didn't observe, I guess, just because of the higher load. So this zone is like smooth between each other, and it's not so well observed like in case of the high cycling fatigue tests. Then it's more spread between each other.
Okay, so you did not observe any stable crack growth regime.
Like in this image, we see the formation of the crack here, and this the propagation zone, and the last stage of the. But it takes about like the half of the sample. So yeah, so it's huge in comparison with the other fatigue testing.
Okay. So 47. Can you go to slide 47? So here you have presented 2 graphs, and in the 1000 degrees Celsius and 800 degrees Celsius, I see at 1000 you see delamination, right? But 800, I suppose you don't see any delamination.
Yes, exactly. For the materials with alumina, we didn't observe this delamination, but you see that this weight gain, it's quite small. In case of the 1000, it was clearly observed for the material without alumina. And on the last stage of the materials with small alumina content, we observed this like delamination. But I agree with the Professor Lazurenko. We need to also measure the weight of the outer delamination oxidized scale. But we realize it after the test. So we follow the standard, but we analyze that it's really important and essential information. And of course, it should be. It's interesting to analyze also the weight of these oxidized scales. But yeah.
Did you also do multiple samples?
What?
Multiple samples? Did you do multiple data points?
We made 3 samples per each state.
And you got very low error?
Yes, yes. There are the error also actually presented. I don't know.
Okay, yeah, I can see some.
So actually, but it's really small.
Oh, okay, so it's very small. But what happens at 1000 that delamination occurs? Because I guess the products of oxidation are similar at 800 and 1000, right?
Yes, but the oxidation process goes more intensive, and in case of the so it's more visible just in case of 1000 degrees Celsius, where we see the formation of this chromium and magnesium oxide, and the last one is the oxide is typically like the delaminate from the material. So we need to prevent the further formation of this material, which can be
okay. So like, there is some misfit that grows, right? The misfit of the oxide layer and the specimen is increasing in 1000 degrees Celsius.
Yes,
which is
yes.
causing this delamination. Okay, I get that. Okay, and slide number 42. Sorry, let's go with that. So HPT, yeah. So this one. So here you measured the grain size and the hardness, right? There are two things. Now, I would assume that at the center of the pellet that you have, there will be very different grain size. Or was it the same as that you find at the edge?
For HPT process, no, it's quite homogeneous grain.
It's quite homogeneous.
Homogeneous. After 8 turns, yes. And we see it's according even for the micro hardness response. For the first stage, this image, TEM image, was present in the middle of the radius, but generally we conclude that it's approximately the same grain observation for the whole samples, since we observed the same micro hardness response.
So you saw micro hardness the same along the radius?
Yes, yes, but the images we presented only on the half of the radius.
Okay. And did you also look at the stress state during high pressure torsion? What is the stress state of the sample? Because you have a high pressure being applied around 6 GPa, is right? That's right. And you are doing these turnings, right? So what is the stress state it is subjected to? What is the stress distribution? Do you see it being homogeneous all around? Or do you see higher shear stresses compared to normal? Of course, normal stresses are not going to change the plastic deformation aspect. But what really, where is the maximum shear stress that you observe?
So like the shear stress along the cross section of the material.
Right. Yeah, so it should vary, right? Because your center.
Yes, but after the specific number of the turns, there are still in homogeneous.
The strain can be stresses are homogeneous.
Yes, the beginning, the higher deformation is achieved at the
periphery.
At the corner, yes.
Right.
But in the center, it can be achieved with the increasing of the number of turns.
And that is because of what do you think that's because of? Why does it become homogeneous?
Because there are we still have the small deformation level even in the center, but it's not so high as on the corner on the samples, for example, after 1 turn. But even after several turns, there are we can achieve the strain level similar in the center. It will be similar as after, for example, 8 turn, as for material after 2 turn and the end of the sample.
But I didn't get that. How is, I didn't understand what you meant. Can you go again? How Why does the stress become homogeneous? Why does the strain become homogeneous with multiple turns? See, first turn, you're saying that there's going to be a stress gradient, right? Yes. And why does the gradient become more homogeneous? Why does the stress or strain become more homogeneous with multiple turns? Is there a reason for that? Can you think of something?
Because the deformation anyway distribute to the center to the center of the sample also.
The deformation distributes from the edge to the center because of strain hardening or because of strain hardening?
Yes, because stretching of the material. And
okay. Thank you. I think that's about it.
Thank you very much. Good questions. So I have only one formal question for Professor Narayan. Are you satisfied with changes introduced to the thesis after the review?
Yes.
Yes. Thank you very much. Okay, so we continue, and I'd like to bring our microphone to Berlin for Dr. Tatiana Mishurova. Tatiana, do you hear us? We see you.
I hear you. Do you hear me?
Yeah. Everything okay?
A bit loud background. I hope it's okay. So I can start, right?
Yes, sure.
Yes, okay. Thank you. Thank you very much, Yulia, for a nice presentation and really amazing work. It's been already a lot of questions, so I will try to be fast. So maybe go to slide 33.
Number 3?
33.
23.
A bit more about fatigue.
23?
No, 33. 33.
Sorry.
No, 33. Yes, thank you. Or 34, better.
Okay.
Next one, yeah. Yes, I was wondering which near-surface defects you meant and why it's like more near-surface defects in unmachined samples and how they're produced.
We didn't make the additional investigation, but according to the literature, it's because of the near surface effect. Then the particles involved to the solid parts. It's one of the reasons, and the second reason it's like the second scanning track, which usually add for the increase the accuracy of the decrease the roughness of the material. So there are like the specific scanning strategy applied to this near surface zone.
So you applied contour scanning, you mean?
In our case, we applied, yes.
Yes, okay. And so by defects, you mean both roughness and like manufacturing defects as porosity and so. Right.
Sorry, could you repeat?
By defects, you mean both like surface roughness, so unmolten particles, let's say, and the manufacturing defects as porosity. You hear me?
So why is there any difference in microhardness, do you mean?
No. I mean, you mean like defects. Here you say defects are like surface roughness plus porosity. I'm just double checking what you mean.
So Tatiana, we have some problem.
You don't hear me?
With the sound, sorry.
Oh, yeah, could you please repeat your question?
It was not question, actually. It was like more confirmation. So let me ask the next question, maybe. How can you optimize porosity, you think, here further?
Okay. I know from observation of the Borisov scope that it's possible to optimize with the different scanning strategy of this to minimize, let's say, of the porosity volume at this near surface zone. But still, it will be higher in comparison with inner materials. Also, another study which was made in our group, they applied to the as-built part. They applied to the laser. They remelt the surface with the laser, and it was provide a really good result, which demonstrate that the fatigue life is higher than in comparison with conventional alloys, but it's move it curve to the conventional materials. So it's how it can be. In our case, we just removed, so turned our samples, and that's how we remove the near surface defects. But generally, it can be decreased a little bit with the scanning strategy, depending on this, and with the further ways to optimize the surface of the samples, like the remelting of this surface. Yeah.
Did you also consider to apply photostatic tracing to the material?
For these materials, in our case, no. But in other study, this was applied to the austenitic steel, and it provided the really good result.
Okay, thank you. So I don't have questions anymore.
Thank you very much. So, Tatiana, I have one formal question. Are you satisfied with the changes introduced to the thesis after the review?
Yes, I am.
Thank you very much. I got it. So, and finally, let me come to jury chair. This is myself. So I have only one question. In introduction, you mentioned that the main advantages of the high entropy alloys is that the ductility of these materials increase increase for cryogenic temperatures. Could you please explain this effect in terms of microstructure evolution, how we can increase ductility for cryogenic temperature?
Because, as I mentioned, we switch for these materials, the deformation mechanism is switched from the planar dislocation to the nanotwinning process at the cryogenic temperature. So, in case of the cryogenic temperature, let's say the dislocation can't move and that's how this deformation process block, and but it activate the process of nanotwinning, and in this case the process of nanotwinning provide this high ductility.
Okay, so thank you. So, and let me say regarding the formal question, I am satisfied with the changes introduced to the thesis after the review. So thank you very much. And now we finished questions from the jury. So therefore, let me invite our audience here in this room and in this Zoom for questions. Correct. You're welcome for questions. Correct. In Zoom, do you hear us? Do you have questions? Audience? Okay, so there are no questions as I see. So then let me give the word to supervisors. Igor Vladimirovich, do you hear us?
Yes, I'm here. Hello, everyone.
Yeah,
I see my I see my colleague from our center. Hello for us. And it's my pleasure to recommend Yulia Kuzminova for the Thesis Defense jury at the CrFeCoNi University. As already discussed during this meeting, actually, three-dimensional printing and subsequent fast structural features of high-entropy alloy are challenging topic for research, but I would like to characterize of a PhD student. During her postgraduate studies, Yulia Kuzminova has developed as independent researcher capable of conducting independent project. I hope she will be a good scientist. She took an active part in the different scientific project grants of our laboratory. She has worked in a number of applied projects. I think and I see that she has a deep background in the material science that will be perfect for her future activity. It's maybe research, it's maybe teaching activity. She also exhibit excellence public opportunities, public speaking skills in the numerous presentations at the Young Research Conference. And in every instance, she has demonstrated a very high grasp of a subject matter and its applications, hard scientific problems. Personally, Yulia extremely easy to get along with. She support of our people's, our student in laboratory, high competence, and in general very much type of a person one enjoy working with. I wish her all success in future research and career. Thank you for your attention.
Thank you. So I'd like to mention that Igor Vladimirovich established additive manufacturing laboratory for our center some years ago. So therefore, a lot of brilliant work arised from this laboratory under supervision of Igor Vladimirovich. Thank you very much.
Thank you.
So and let me pass the word to a co-supervisor, Dr. Stanislav Yevlashin. You're welcome.
Yeah. Good afternoon, everyone. So I would like to say a few words about Yulia. So first of all, she's a really good person in terms of collaboration, in terms of support for students and so on. And according to PhD defense, you saw what she presented, eight publications, but really she already published in co-authors about 25 publications for 5 years. From my point of view, it's really brilliant results. And also she participated in many conferences. I don't know how many it was, but maybe 10, 20, I don't know. But anyway, and of course, she already independent researcher, and I'm really glad what she decided to continue her way in the science and continue to study metals and other materials and not change the profession after defense. So Yulia, good luck in the future research. And I wish you really brilliant results for Science and Nature journals. So this is all what I can say.
Thank you very much. So and now we immediately come to closed deliberation. So therefore, let me ask all my colleagues leave this room, of course, excluding jury members. So we'll take some time for discussion and final decision regarding the defense. Thank you very much. Okay, today's beautiful day, sir. It's my greatest pleasure to say that Yulia Kuzminova has been awarded by PhD degree in maths and mechanics, and there were no any concerns within jury members. So please take our congratulations, and we wish you your further evolution and progress and in research and scientists. Thank you very much. Yes, Yulia, please take a microphone and say your word.
Thank you. Thank you for your decision. Maybe some question you were not satisfied, but I believe I will go deeper inside to this field and continue to and study and research to develop myself in this field. To be proud the part of this academic community. And I would like to say thank you to my colleagues who's left because they have their business at the moment, but their helpful was it's unestimated because they help a lot to perform to done this work. And also, I would like to thank Professor Zherevtsov as my professor from the university, alma mater university, because all of this maybe not really satisfied you with my question about HPT process, but anyway, all my knowledge and all this result in the publication, it is a result of your contribution to my education as the specialist. And Daria, thank you for your help and also the communication, because it's also inspired me for the new investigations. And thank you, Professor Sergeyevich and Professor Yevlashin, because they support my interest in the academia and help and support of this field. And thank you for coming, Professor. Thank you again.